so good evening everyone, and thank you for joining us today for Professor Kennedy's talk. So it's 7 o'clock, so let's start with the presentation. Before actually introducing Professor Kennedy, let me a little bit go through some logistics, and then we can move on with the talk. So first of all, a little bit about our chapter. Our goal is to help our members take current with new technologies, to inform our community about the latest inventions and innovative ideas within academia and industry, to encourage interaction among world-leading researchers on emerging topics, and to create a forum where participants can network, learn and exchange ideas in a welcoming professional environment. If you haven't already visited our website, using this address, and or you can just search for IEEE SCVCAS. We usually hold our seminars every second or third Monday of the month. In the summer we have skipped a few months, but hopefully in the fall we'll resume again with talks every month. Also, if you haven't signed up to our email list, you can go to our website, and on the left column and at the bottom there is this link to the Santa Clara Valley Circuits and Systems chapter. So for the email list, you can sign up there. Also, before starting, I would like to ask everyone to please silence your cell phones. And if you haven't done already so, to please sign the sign-up sheet, which you can also do before leaving at the end. I would also like to thank Qualcomm for hosting the event, all the volunteers of our chapter for helping in organizing this talk, and of course you for coming here and attending this talk. I would also like to announce our next seminar, which is actually co-sponsored by several chapters here in Silicon Valley. So by PACE, the Signal Processing Society, the Information Theory Society, Solid State Circuits, Communication Society, Magnetic Society, and of course Circuits and Systems. So it's actually a tutorial on low density parity checking decoding, and includes both an algorithmic aspect to it and also hardware aspect to it, so both VLSI architectures and implementations. This will take place in the Convention Center in Santa Clara, and it's part of the Flash Memory Summit Conference. That will be on August 6th. If you are interested in going there, you can find a link on how to sign up and register for this event on our website. And please do so. I think before August 4th, there is a kind of a little bit discounted price to that event, and after August 4th, I think only walk-ins are accepted, which will be a little bit more expensive. So today's talk, we're delighted to have tonight with us Professor Michael Peter Kennedy, who will talk about digital delta signal modulators. Professor Kennedy is a professor of microelectronic engineering at the University College Cork. He received the BE in electronics degree from UCD in 1984, the master's and PhD from the University of California, Berkeley in 1987 and 1991, respectively, and the diploma in engineer from the National University of Ireland in 2010. He joined UCC as chair of the Department of Microelectronic Engineering in 2000. He served as Dean of the Faculty of Engineering from 2003 through 2007, and as Vice President for Research from 2005 to 2011. He has over 340 research publications, including 4 patents in the fields of oscillator design, hysteresis, neural networks, nonlinear dynamics, chaos communication, mixed signal tests, and frequency synthesis. He has worked as a consultant for SMEs and multinationals in the microelectronics industry, and is founding director of the Microelectronics Industry Design Association, MIDAS, Ireland, and the Microelectronic Circuit Center of Ireland, MCCI. He was made a fellow of the Institute of Electro and Electronic Engineers in 1998 for contributions to the theory of neural networks and nonlinear dynamics, and for leadership in nonlinear circuits, research, and education. He has received many prestigious awards, including Best Paper from the International Journal of Circuit Theory and Applications, the 88th IEEE Kelvin Lecture, the IEEE Millennium and Golden Jubilee Medals, the inaugural Royal Irish Academy Parsons Award in Engineering Sciences, and the IEEE Solid State Circuit Society Chapter of the Year Award 2010. In 2004, he was elected to membership of the Royal Irish Academy and was made a Fellow of the Institution of Engineers of Ireland by presidential invitation. He was made a Fellow of the Irish Academy of Engineering in 2014. From 2005 to 2007, he was President of the European Circuit Society and Vice President of the IEEE Circuits and Systems Society. During 2012 and 2013, he was a Distinguished Lecturer of the IEEE CAS Society. He has been Secretary for International Relations of the Royal Irish Academy since 2012. He is currently Chair of the P7 Starry Grants Panel at the European Research Council. So with no further ado, please join me in welcoming Professor Kennedy.
Thank you very much, Dimitri. I guess I used up all my time. Okay, thanks for showing up to this talk. I'm in the area at the moment, a new research grant with two companies in the region, so I'm here working out the details of work packages with them that are committed. There's some other work in this research grant that's as yet uncommitted, so I'm looking forward to questions from you that will help me pin down some of the direction for this future research. The talk is an introduction to delta signal modulators. I noticed by the age that not everybody is a fresh undergraduate, which means you have a lot of experience, and I suspect there's some people here who have a lot more experience in this topic than I do. But let's hopefully share our insights, and maybe we'll learn something together. I came to this topic, my background is nonlinear circuits. As a PhD student, I worked with chaos and neural networks. I came to this topic about 10 years ago because in Ireland there aren't many jobs in chaos theory, and not many students want to study it. They want to do real things. So I moved closer to the microelectronics industry, and I've been trying to look at applications of nonlinear things in the microelectronics field. So we've been looking particularly at digital delta signal modulators, and more specifically at their application in fractional-N frequency synthesizers. So this talk I would like to dedicate to one of your colleagues from this area, William Egan, who passed away a couple of years ago. But in teaching my course on Frac-N synthesizers, frequency synthesizers, I first used his phase lock basics book and then his frequency synthesis by phase lock. And about 3 years ago, he contacted me when he was writing his advanced frequency synthesis by phase lock to ask some questions about our work. And so we engaged in a dialogue at that time. And I hoped very much to meet him when he was to come to Ireland. Unfortunately, he passed away before I could meet him. So I have learned so much from him. I'd just like to dedicate this to his memory. Okay, so digital delta signal modulators. The reason I came to this topic, there's a lovely paper by Marty and Galton from 2007. They state that you can buy textbooks on analog delta signal modulators. There are lots of analog delta signal modulators, particularly in A-to-D converters. But from a commercial point of view, the digital version is far more important in that it's in digital to analog converters and increasingly in fractional-N frequency synthesizers. So pretty much every wireless communications device has multiple digital delta signal modulators. But unfortunately, you can't buy a textbook about digital delta signal modulators, and there are subtle differences between the analog and the digital implementations, such that intuition about one doesn't necessarily carry over to the other. So my background was analog continuous time, and therefore to go into discrete amplitude, discrete time, I certainly learned a lot of things, and I'll share some of the insights that we gained along the way. So the talk is broken into three pieces. The first piece is what you teach the student in college. That's what the ideal DDSM looks like. That's why it's so promising. That's why we love it. The second section is about the problems that happen in real DDSMs, and in particular, the issue of spurs. This is what makes the DDSM so difficult to use, and there's a lot of, I say, engineering best practice about how to minimize spurs, but there's also now a lot of good analysis which can be used. And I'll speak at the end about some of the research we're on at the moment and some of the open problems we're looking at. So, the ideal DDSM, first the big idea, then the signal processing assumptions, and some of the applications. The ideal DDSM is a block that takes a long word on the left-hand side here, X. You take a long word and you convert it into a short word. Now, going from a long word to a short word, there's necessarily quantization involved in that. But the quantization noise is shaped, it's high-pass filtered, and then later you can remove that, later in the signal processing channel, either you or somebody else will remove that high-pass filtered noise. So you go from long word to short word, and as I say, add this quantization noise that's high-pass filtered, and then later removed. Now, here's a typical signal. This is from Mike Perrott. Signal that's two-level signal, average a half. You can see that the average is a half, and it's a sine wave, so you can kind of figure out that there's a sine wave in there somewhere. Now, the book says that this should look like a sine wave, so it should be a tone, and then there will be the high-pass filtered quantization noise shown in blue. So you have your quantization noise here, shaped high-pass filtered. The idea is that you later come along with a low-pass continuous time filter and take out all the high-frequency stuff, so that in the frequency band of interest, you have just added a little bit of quantization noise. And if you've done this right, you have very small degradation in signal-to-noise ratio. So that's the basic idea, and this is the picture you'll see in the book. Now, that's the analog case. The digital case is a little bit different in the sense that the signal you started with was already quantized. So there's a noise floor associated with that original signal. And then, once again, you add the shape quantization noise, and you come in with your low-pass filter, and you take everything out. But here, in principle, you might be able to have no degradation in signal-to-noise ratio, in the sense that the added quantization noise might be completely masked by the original quantization noise flow. That's a subtle difference between the two, but in theory, you might have no degradation in signal-to-noise ratio. Okay, so why do you bother? I mean, you have a nice long word representation of the signal. Why do you bother going from a long word representation to a short word representation? And the main reason for doing that is to make the job of the analog circuit designer easier, so the analog circuit designer can build a 1-bit linear converter rather than a 16-bit linear converter. So going from large number of bits to small number of bits is really about making the job of the analog designer easier. The oversampling, and it's natural in these systems to have oversampling to push the noise away from the signal band. The oversampling really is about making the reconstruction filtering easier. So you're making the job for the analog designer easier in two ways. Linearity specs are relaxed, and also the filtering roll-off specs are relaxed. Now, underlying all of this, although we seldom mention it, is what's called a classical model of quantization. And those of you who are following this field will know there's a book came out recently, a very thick book by Clara and Bernard Woodrow on quantization noise. It's a very nice book. It'll take you many, many hours to read, but it'll tell you everything you need to know about quantization noise. So this classical model of quantization, we assume that that applies. The classical model of quantization says that the quantization noise is statistically independent of the signal, that it's, in our case, uniformly distributed over one quantization interval delta, and that it's stationary with a flat power spectrum. So, again, if you read the quantization noise books, the classical model of quantization applies basically when you're traversing the quantization levels regularly. So CM2 can be applied when the quantizer input traverses several quantization levels between samples. Now you'll see later, this will be an issue in some of the DDSM applications, particularly in channelization in the Fractional-N synthesizer when you're trying to keep the input to the DDSM constant. Okay, so in the Z domain, you have an output Y, YZ here, which is the signal transfer function times the input X plus the noise transfer function times the quantization X. And in the simplest implementation, the signal transfer function might just be a scaling. It could be a delay, but it's typically all pass, and the simplest, and what I've been talking about, is just a scaling. So you're scaling here, and then the noise transfer function is typically a high-pass filter of this form. I use this repeatedly. It's 1 minus e to the minus 1 raised to the L power. So that's our quantization noise filter, noise transfer function. So the picture again, the output is a scaled version of the input plus the quantization noise shaped by this filter. This is the original signal going in. It's discrete time signals, so they're aliases at multiples of fs. And then the quantization noise has this typically 1 minus e to the minus 1 raised to the L power shape. Now, the pictures that I'll be showing repeatedly are how that quantization noise is shaped. So if you look at the expression for the power in the quantization noise, it looks something like this, which at low frequencies scales roughly as f to the power of 2l. So you will see me drawing pictures where I have on a log-log scale of linear slope here. This is a slope of 20 LdB per decade. That's the shaped point quantization noise close into the signal. Now, there's a simulation of the same thing, and you see that the simulation follows that classical model of quantization. So that's what we'll be looking at, these 20 LdB per decade. If it's second order shaped, we'll be looking at 40 dB. If it's third order shaped, we'll be looking at 60 dB per decade. So the picture again, there's our original signal with a quantization noise floor associated with the original quantization of that signal. The high-pass filtered noise come in with the low-pass filter afterwards, remove the quantization noise. Now, where is it used? I said that, or Marty said that from a commercial point of view, it's extremely useful. The first application was probably the oversampled DAC in CD players. We're all old enough to remember the CD player when it first arrived. So the idea there was to get down from, say, 14, 16 bits down to 1 bit so that you could have a linear, completely linear analog DAC. That was the original application. The Fractional-N synthesizer came in the 1990s and is pretty much universally used today. Class D audio amplifier is becoming more and more important. As we go forward, probably video channels will all become oversampled signal delta sigma, and the audio channels will go as well. The power channels will go. So here's there's an analog devices part. Class D digital audio power amplifier, and you see the big digital words are coming in this end. They're coming in serially, actually. The big digital words are coming in this end, and then they're going through the digital delta signal modulator, reducing the number of bits to drive a power bridge and drive the loudspeaker. Signals in such a system might look like this. You'll go from a large number of bits through a DDSM down to a smaller number of bits, then maybe through pulse width modulation or something else, down to fewer bits again to drive a bridge. There's your signal, for example. There's the shaped quantization noise with that characteristic 20 LdB per decade shape. There's a whole bunch of high frequency jump here associated with the pulse width modulator and other parts of this circuitry. But your low frequency, continuous time, whether it's filtering before the bridge, filtering in the bridge, filtering in the loudspeaker, whatever, you'll take that stuff out. Another one, the oversampled DAC, is another analog devices part. Again, 16 to 24 bits in here. You go through ultimately through a multi-bit digital delta signal modulator down to fewer bits in the DAC. The job of the DAC designer is easier because the linearity specs are relaxed. And you see too the oversampling. There's the oversampling. So as I said, the two things you're getting typically with the DDSM, you have oversampling and DDSM relaxing filter roll-off and typically linearity specs in the analog components. The third application, and the one I'll speak most about, because I'm most familiar with this one, is the Fractional-N frequency synthesizer. This is the original patent from Riley in 1990. And the idea is that you have a phase-locked loop, you have a reference, a crystal reference frequency here, for example, very precise reference frequency. The output frequency from the VCO is divided down. Let's imagine that this was just an integer. Well, then if that's divided down by an integer, and this frequency is locked to that frequency, then the output frequency will be an integer n times the reference. And so with an integer n frequency synthesizer, you can set output frequencies that are integer times the reference. The advantage of that is that with that single integer, you can set as many frequencies as you want. The disadvantage, primary disadvantage, is that the spacing between those frequencies is the reference frequency. So if you want the frequencies to be closer together, you have a problem with this. The Fractional-N synthesizer solves this problem by, instead of dividing by a constant integer n, the divider number is modulated by this block here, the delta signal modulator, so that, say you're dividing by n and n plus 1, n, n plus 1, n, n plus 1, then the output frequency will be, on average, n plus a half times the reference. And so you could have a step of half the reference frequency instead of the reference frequency, instead of full reference frequency. So what the modulation of that divider number by the digital delta signal modulator allows you to take frequency steps here that are a fraction of the reference. So you get all the advantages of the original integer n synthesizer, now you can take small steps as well. So here's an example from, this is actually from Analog Devices data sheet. We have a reference frequency here, 13 megahertz. This is for a GSM application. You want to produce 1800 megahertz. So how do you do that? You divide down by this number here. There's an integer part plus this number y. There's a small integer as well. This is the output of the DDSM. The DDSM has a word length n. You apply an input x, and the average value coming out of the DDSM, the average value of y, is going to be x divided by 2 to the n. So this guy now will allow you to divide here by integer plus this fractional number. The fractional number is x divided by 2 to the n times f. So the DDSM is controlling this part, and it's setting the average division ratio to a fraction of FREF. And so by varying that number, by making that number large, you can make very small steps, and then x is just determining the value of those. So the frequency resolution here is now determined by the word length of the DDSM, and you can, commercial parts today are up to 24 bits on that number here. Okay, so here's that part again. The output frequency is the reference frequency multiplied by the int plus frac divided by mod. There's our third order digital delta signal modulator. There's the counter, whose count value is being modified to n plus the value coming in from here. There's the integer part, and here are the mod and frac parts. That GSM example, if I want to get 1.8 gigahertz from 13 meg, there's my int, frac, and mod. And you'll see here that I get F out is 1800 megahertz, and the smallest step that they can take is going to be FREF divided by 65, which in this case is 13 meg divided by 65 is 200 kilohertz. Is my channel spacing for the GSM. Here's another part from Maxim, and you see it's the same deal. There's the modulator, there's the frac part, the modulus, the integer part, and the output frequency. Output frequency is n plus frac divided by mod of the reference frequency. Now, I mentioned that the output frequency is going to be, on average, n plus f over m. But instantaneously, you're dividing by different numbers in the feedback path. And because you're dividing by different numbers in the feedback path, that shows up as phase noise in the output. So the disadvantage of or potential disadvantage of the DDSM and the Fractional-N frequency synthesizer is that this jitter is going to show up as phase noise at the output. There's a lovely paper by Mike Perrott from 2002. This is the Mike Perrott paper, where he builds a model of the full Frac-N synthesizer and says, okay, how do those various contributors show up as phase noise at the output? And he lumps the sources into three groups. So the first group here is the red piece. The red piece is the physical component noise in the phase frequency detector, the charge pump, the loop filter, the divider. So all of that physical component noise is white or whatever shape you want, but that's the noise, physical noise associated with those components. Now, there's also an update associated with the reference clock, and that update reference is an update on the edges of the reference clock. That means that there is a very strong tone coming through here. This is the reference tone, which in the synthesizer produces a reference spur. So that has to be included as well. Over on the VCO, far away from the carrier, the phase noise of the VCO falls off at about minus 20 dB per decade. So that's the blue piece over here. And then we'll consider what happens to the noise the quantization noise, shape quantization noise that comes in from the DDSM. If you look at those, you see that all the internal noise sources and physical components, they go through the low-pass filter characteristic, low-pass closed-loop characteristic of the loop, and then appear at the output. So this red noise is going to be low-pass filtered before appearing as phase noise at the output. The VCO noise, far away from the carrier, that's going to be high-pass filtered before it appears at the output. And the noise from the shaped quantization noise from the digital delta sigma modulator goes through low-pass filter and it's integrated. So it's integrated once to do a phase, frequency to phase conversion, and then it goes through this low-pass filter before it appears at the output. So if you look at how those components then show up in the compound output phase noise, the component noise was this red stuff along here, and that has been low-pass filtered. The VCO far away is this guy here, and that was probably going up with 1 over F noise and other stuff in here, but that's high-pass filtered, so that can be killed in here. And therefore, the envelope of what you see at the output will be the component noise, and you've done the best job you can on that. That's here. And over here, you've done the best job you can on the VCO, so you can't do better than that. And therefore, that's what you're going to have, even if the DDSM were not there. Now, the DDSM is there, but the DDSM noise is coming up here, shaped first at 20 LdB per decade, but it's integrated once, so it's coming up at 20 L minus 1 dB per decade. And provided that your loop filtering is of sufficiently high order, you can turn that back and filter it and hide or spectrally mask the quantization noise associated with the DDSM and hide it below the envelope that was there anyway. So the attraction of the Frac-N synthesizer is that quantization noise is first high pass shaped, then a low pass filtered by the loop, hidden behind what was there anyway, and so you get all the advantages of the Frac-N synthesis for free. That's why it looks so attractive. So, the big idea, linear all-pass signal transfer function, noise transfer function attenuates the quantization noise in the signal band. We've assumed that the classical model of quantization applies, that the quantization noise is uncorrelated with the signal, and I've mentioned these applications. So that's what you'll read in the book. Unfortunately, it's a little bit different in practice. So I'd say something about what happens in practice. I'd say something about the DDSM architectures, the spurious tones that upset people so much, and some techniques to minimize those tones. So, first, let's be sure that we did everything right. The output, we said, depends on the quantization noise. This is the formula we had. Y is signal transfer function times X plus noise transfer function times E, where E is the quantization noise. We said that the signal transfer function we'll see that we can do a simple scaling if we want. The noise transfer function is going to be of this form, 1 minus e to the minus 1 raised to the nth power. Now, the simplest possible case is the first order modulator. I was looking at the data sheet of one of the TI parts today, and it says that you can actually input the first order modulator in the Frac-N synthesis. So, let's say you decide to do that. Y is 1 over mx plus, we'll now have 1 minus e to the minus 1 times the quantization. To do this, you build a very simple block. It's just just a digital accumulator. The digital accumulator takes the input word x, adds to it a value stored in a register here, and just keeps accumulating. The overflow comes out here. This is the carry, and in the notation I'm using, the carry is y, is the output. So x is the input, y is going to be the carry out, and the signal that is stored in the register, we'll call that s, that'll be the state. But basically you have, you're just adding here, you have an adder and a register, and then you have this very hard nonlinearity that overflows when you hit m, which is the modulus, that's the 2 to the power of n in an n-bit implementation here. So I have a first order, and it's called an error feedback modulator. This block is called an error feedback modulator. It's called an error feedback modulator because we feed back the error rather than feeding back the output. X in my notation is the input, Y is the carry out, and S is the state, and N is the modulus. This is a circuits and systems talk, so we start doing systems block diagrams. So our system block diagram of this, here's our input X, here's our output Y. The nonlinearity here is represented as this quantization function Q, and just to keep everything right, I have a scaling here M, and there's the signal B. There's the register on the way back, and there's the state S. If you write this as a nonlinear dynamical system or as a control system, the next state is the sum of the current state plus the input modulo this number m, the modulus. And then the output y is the readout function, the nonlinearity applied to input plus s. Now, here's where the typical simplification comes in. We don't like to deal with nonlinear blocks, and therefore we now apply the classical model of quantization. And the classical model of quantization says take out that nonlinear block and replace it by the appropriate scaling plus additive quantization noise. So here's our classical model of quantization, and here is now our linear system. And there's the quantization block Q applied to its input is just a scaled version of V plus whatever quantization noise was added. Now, I'm going to use the notation EQ everywhere. Many places in the literature, they do things based on this E down here, this error here, but there's just a linear relationship between E and EQ, so don't worry about that. If you check the math and say, why is this quantization applied to x plus s, and you work everything out, you find that y is indeed 1 over m times x plus current quantization noise minus last quantization noise. And that's exactly what we wanted to implement, and that's exactly correct. So this block, and those equations implement exactly the error feedback, first order error feedback modulator. That's it. In the z domain, yz is 1 over mx plus EQ 1 minus c to minus 1 raised to the first power. And there's our little model, and everything is correct. Now, you go simulate this, and unfortunately life isn't so nice. There's our original signal, average value of 0.5, and there's a sine wave in there. In the frequency domain, we were expecting to see a lovely tone and shaped quantization noise. The quantization noise should have been first order shaped white noise. But it's clearly not first order shaped white noise. It's a whole bunch of tones. These tones are spurious tones or spurs. The audio people call them idle tones. They are a whole bunch of tones. It's not first order shaped noise. So that's why pretty much everybody walks away from the first order modulator and says, no, we use higher order. So higher order noise shaping architectures, these come in two classes. There's the single quantizer version and the multi-stage noise shaping version, the MASH. Single quantizer, as it suggests, has a single quantizer. There's a filter in the feed-forward path, filter in the feedback path, a single quantizer. They're great, but they're great because you can shape the filter characteristics of the noise transfer function, signal transfer function. But the disadvantage is that if you're not sufficiently experienced, they might be unstable or they might give you full dynamic range. So the MASH is more attractive because it's kind of foolproof. It's a feed-forward structure. It's unconditionally stable, and if you do it right, you get full dynamic range as well. So I'm just going to talk about the MASH structure. And the MASH is very easy to build. You just take these basic first-order stages, and that's just a digital accumulator, and you cascade them. You take the output of the first stage and feed it as the input to the next stage, take the output of the next stage, feed it into the next one, and so on. Just cascade a bunch of these. You're going to make it second order, there's two of them. You're going to make it third order, there's three of them, four of them. It's very easy. And then you just combine the outputs with appropriate filtering to produce the final output Y. So signal X goes in here, signal Y comes out. And this structure implements exactly what we want here. Y is a scale version of the input plus quantization noise, 1 minus e to the minus 1 raised to the Lth power if you have L sections. Now, there's again a difference between the analog version and the digital version here, in that in the analog implementation of a MASH structure, you have to worry very much about cancellation, exact cancellation of intermediate components. Here, the cancellation is exact. And because the cancellation is exact, the quantization noise only has one component, and it's the quantization noise associated with the last error feedback modulator in the chain. The quantization noise associated with all of the other blocks, they're all cancelled exactly. So you only have to deal with the quantization noise from the last guy. Now,
in your experience, how many stages you use?
You will see. Okay?
This is N, right?
This
N
is
stages.
This is the next one. Yeah.
You don't want to use infinitive, right?
I like 3. Okay, and you'll see why. Okay, so you can have as many stages as you want.
But in reality, you don't want to use so many. You want to optimize to.
Correct.
So what's the point? What's the number?
3. You'll see why it's 3. Okay, the intuition about the first order stage was classical model of quantization wasn't working correctly. Okay, there's some correlation between the signal and the quantization noise. So there's some correlation between that signal and that, this signal and that quantization noise. But if we run it through another one, maybe there's less correlation here, there's less. As you go further along the chain, maybe it gets better all the time. So by the time you've gone through a few stages, maybe the quantization noise here isn't so strongly correlated with the signal, and this will give us better performance. Okay, that's the intuition. Okay, you will notice, and we'll come back to this later, in each of these blocks, I have labeled the state of the first stage at time 0, the state of the second stage at time 0, and so on. So I've given the initial state of each of these blocks. You'll see that's important as well. Okay, the MASH, we'll be looking at second and third order filtering, and we should see shaped quantization noise that looks like this, second and third order shape. So, here's the second order stage. So second order stage, this is a second order MASH. You'll notice it still has a DC level of a half. There isn't a pattern of the sine wave anymore, so this is looking more noise-like as we want it. And indeed, when you look at the spectrum, there's our fundamental tone, and there's the shaped quantization noise, second order shaped. Okay? So the second order modulator is looking good. If you go to third order, the thing looks even better. This, I don't see a sine wave in there, and this thing looks like nice shaped quantization noise. Okay? So I'll go further and further and further, but let's stop at 3 for the moment. Okay? So we'll stop at 3. Therefore, I should see 60 dB per decade shaped quantization noise like that. Well, unfortunately, if you do a MATLAB simulation of this, MASH 111 with this is an 18-bit implementation, constant input, and an even initial condition. In other words, start all those registers with zeros. You don't see that shaped structure. All you see is a whole bunch of tones. And if you notice in this picture, those tones are 40 dB over where you expected them to be. So you did the third order, but unfortunately it didn't look like you expected. The audio DAC, they're idle tones. Input is quiet, or input is slowly moving, and you have a whole bunch of tones in this thing. Here's some work we did. Here's a simulation using a theoretical model. There's a full Verilog AMS model of the synthesizer, and here is the measured output, and they're close enough. Here's the same thing, but we don't see anything in the linear model. We see a whole bunch of spurs in the full behavioral simulation, and we see a bunch of spurs in the experiment. And the only difference between these two simulations is that one started with the registers 1, 0, 0, and this one started with the registers 0, 0, 0. Okay? So this is kind of a nightmare customer return. I tested it in the lab and it works. Customer tested it and it doesn't work. And we both tested it, only one put all zeros in the registers and the other put a 1. Okay, so this is the bad news about the DDSM. Different word lengths here produce different spectra, different inputs produce different spectra, different initial conditions produce spectra, and all of the above can produce spurs. Here's an example of different word lengths. There's an 18-bit and a 9-bit implementation. You'll see that the 9 is not so nice. Here's different inputs. This is probably the scariest one. There's the theoretical curve. That's what we expected. This guy here, the gray stuff, is the initial, that's with the input x equals 1. And these two big guys here, that's with the input equal to half scale. So it's a third order MASH, input equal half scale, and all we're getting is these two big tones here. Here's different initial conditions on a linear scale, so it looks terrible. That's the theoretical curve. The blue is the odd initial condition. The green is the even initial condition, and we don't want to see that. So, what's the problem? The problem is, this is a finite state machine. And a finite state machine can do simple things like ping pong back and forth between a couple of states if you're unlucky. If you're lucky, you might travel around a lot. So the fundamental problem with the DDSM is that you get these short cycles where you ping pong between a small number of states, and that produces the spurs. The classical model of quantization was applying when we were traversing multiple levels, basically when the input is constant or slowly moving, or, as we've found more recently, when it's periodic at certain periods, you can get these strange behaviors. So, as I mentioned, the fundamental problem is it's a finite state machine with a total of NS states, and there's a deterministic rule that says if I'm in this state with this input, then the next time the clock ticks, I go to that state. So worst case, I'm in this state, next time the clock ticks, I go here, I go back, I go here, I go back. That's it. In the third order MASH, our favorite, when the input is fixed, most complex trajectory you can get is when you visit all but one state. It's a bit like the linear feedback shift register. There's one bad state, but everything else goes back to you visit everything. In the worst case, that third order MASH is just going to cycle through 4 states. And that's the picture we saw. That's the Fs over 4 when you're half scale and you just cycle across 4 states. So, I teach our signals and systems class to our students, and one of the things we teach in signals and systems is Parseval's theorem. And everybody says, what's Parseval's theorem for? And I couldn't answer for many years, but now I have a beautiful example. Parseval's theorem says that the power in the time domain equals the power in the frequency domain. We know what the quantization noise is in the time domain, so we know the power in the time domain. That power in the time domain has to be spread over a number of tones in the frequency domain. If we have very short cycles, we have very few tones, lots of power per tone. If we have very long cycles, we have lots of tones, very little power per tone. So, short cycles, large tones, spurs. The quantization noise is distributed over n tones. More tones you have, fewer tones you have, the more power per tone. And that's the fundamental problem with the DDSM. It's inherent in it. Okay, so we know what the problem is. Now we have to fix the problem. When the cycle length is short, quantization noise is distributed over a small number of tones, therefore high average quantization noise per tone. To solve the problem, we have to maximize the sequence length, maximize the cycle length. If we can maximize the cycle length, then we get that quantization noise per tone down, and we get closer to the theoretical performance. There are 2 ways of doing this. The first one is, I know nothing about the system, so I'm just going to shake it. That's the stochastic approach. The second one is, I know what the cause is, so let's eliminate the cause at source. That's what I call the deterministic approach. So first, the stochastic approach. The problem was that when we were in this state with this input, we always moved to the same next state. In order to break up a very small pattern, I basically have to make this rule random instead of deterministic. I can do that by adding a dither signal. So next time I'm in this state, the dither might be different and I can go to a different place. And that's what dither is all about. You just add a random component every time you get to a state, and that random component might send you somewhere else the next time. You break the periodicity, and therefore you can get these longer trajectories, less power per tone, and you clean up your signal. So it turns out that most techniques that are in the literature can be reduced to some variant of this, which is additive least significant bit dither. Here's my input signal. I take a dither, a 1-bit dither signal, and add it, and then basically randomizing the input, and that hopefully randomizes the output, breaks up the patterns in the output. I've shown here a filter VZ And the filter is typically of the form 1 minus e to the minus 1 raised to a different power, r. I'll show that. So what happens? This is our 18 and 9-bit before, 9-bit without dither, 9-bit with dither. It works, right? So dither is great, and that's why everybody loves dither. But you'll notice some little funny things with dither. We'll come back to those. This is the data sheet of an analog devices part. There is what's called the lowest noise mode, and you see these big spurs, and then you turn on the dither, and you go to the low spur mode, and in the low spur mode, the spurs are gone. However, you get a little bit more in-band noise. So this is a maxim part. Here's the low noise mode with the spurs, and here's the low spur mode with a little bit more noise. So what's going on? Input signal, dither. Gosh, dither goes the same way as the input. The input was just an all-pass, maybe just a scaling. So we should see at the output just scaled noise. And that's indeed what you see. So here's the no dither case. Here's the white noise with no scaling on it, with no filtering on it. And then here's, I do first order filtering to the white input noise. So that's great. There's the third order theoretical limit. There's zeroth order shaped dither, first order shaped dither. You think, okay, all I do is I keep ramping up the order of the filtering of the dither, I'll take it up to second or third order, take it up to third order, and I'll hide it down here. Unfortunately, that doesn't work. And again, Marty and Galton have proven theoretically, so it doesn't work. There's the MASH 111. Here's the third order filter, and of that's the noise shaping filter. And then the best you can do in terms of dither is first order. If you try second or third order, you get regrowth of spurs back in the spectrum. So, in fact, that paper by Martin Galton says that in the third order case, the best you'll be able to do is this. All right? And what determines the level here, so the level here or the level here, is determined by that factor 1/n. So make your modulus larger, make it 25 bits instead of 24 bits, and you go down here. Okay? So you can push that level down by adding more bits to F. But that's, from a theoretical point of view, with dither, that's the best you can do, according to that paper. Okay, you can also, if you don't want to do the add a bit of noise and shake it, you can do the deterministic approach, which is, I know what causes the problem, so let's eliminate it at source. One of the causes of the problem is even initial conditions. So you can eliminate this at source by setting the least significant bit of the first EFM to 1 or any other odd number, and then it'll always give you maximum length sequences. Now, different companies have different magic numbers that they put in as a seed, but from a theoretical point of view, all you need is that S10 should be odd, and that's the seeding, and that'll always give you the best case. But from a philosophical point of view, that doesn't. I don't like that, because why should I have to reset registers every time I want to choose a new band? Anyway, this is the theoretical result with the third order modulator and an odd initial condition. You'll always get sequence lengths that are 2n. Maximum inner guaranteed to be 2n. We have another approach to this. Some work we did with, so we mentioned S3 earlier, some work we did with S3 in Ireland, where we reset, when the output rolls over, we reset the input, we reset the register not to 0, but to a prime number away from the top of the scale. And that structure gives you, in the third order case, you get sequence lengths that are of the order of modulus raised to the order of the structure. So the third order structure is going to give these very large sequence lengths for all inputs, for all initial conditions. Basically, it's the theoretical solution. So there's the theoretical limit, the black curve. Here in the blue, there's a sine wave applied in this case. So the green here is 0th order dither. The red is the best you can do with shaped dither, and the blue is our structure that hits the theoretical limit. So as far as we're concerned, that problem is solved. Okay, so that's the real DDSM. It's nonlinear. The classical model of quantization doesn't always apply. The spurious tones are coming from constant or periodic inputs and indeed periodic inputs, causing periodic quantization noise. Shorter cycles give higher power per tone. The cycle lengths depend on the input, the initial conditions, and the word length. If you want to minimize those tones, you can add filtered dither, or you can select the input, initial conditions, or modify the architecture.
Question. So we can do both, right?
You can
add the filters, dither, and also.
Correct. So you can. I'll show you later a part that we've implemented, and we did first order shape dither, and we also did odd initial condition.
Also, I remember when you have different order, you may get to the stability issue. Not stable for this.
Not with the mesh. With single quantizer, yes, but not with the mesh. The mesh is unconditionally stable because it's a feed-forward structure. So that's the beauty of the mesh structure. You don't have to worry about those things. Okay, so some of the things we've been doing more recently, I mentioned error masking, bus splitting, and mixed radix divider controller, and then some of the work we're doing on dither and nonlinear. Okay, the first one is that insight about you're adding shaped quantization noise, and then you or somebody else is going to remove it later. If that's true, then you can hide all kinds of other junk in the same place where that stuff is going to be removed. We said that there's the signal piece that you want, and then there's this shaped quantization noise term. So that's going to be removed by you or somebody else further along the signal processing chain, and any additional quantization noise that lies below the mask of that shaped noise will also be removed by that filter. So here's the picture, and I'm imagining a sine wave coming through here. Here's my quantization noise floor. I can't do anything about that. Here's what I was going to do in terms of quantization noise of the DDSM anyway. So basically, anything I hide in here will have no effect. However, I might be able to use some of that hidden stuff to give me performance advantages. There's the basic idea. I can't do anything about that. I can't do anything about this. But there might be some first order and second order shaped pieces, and if I can control where they are, if I can hide them down here, they will have no negative effects. We're going to look at two techniques. The first one is intrastage quantization in the MASH, and the second is a technique called bus splitting. We might be able to reduce area and power and potentially increase speed. So here's the first. The basic MASH structure has three identical stages, and the outputs of these guys are combined to give your final output. Now, those of you who design analog ADCs, MASH ADCs, know that you put more effort into the first stage than the others. And there's an equivalent of that in the digital domain, which is the following. Those three blocks have the same word length, and therefore the hardware is going to scale as 3 times the word length. But how about if you do something different? In the first stage, we'll have n bits internally in that stage, but we'll only pass m of those to the next stage. And then we'll take m of those and pass l of them to the next stage. So there's an interstage quantization here, another interstage quantization here. If you do that, then those stages are, you have decreasing word lengths, and the hardware requirement is going to scale less than 3n. It turns out that this is optimal. You can get the same performance with everything hidden. Basically what happens, there's your first stage is unchanged. The second stage has an interstage quantization in it, and the third stage has an interstage between 2 and 3. But that's what you wanted. Why was the scaled input plus the quantization noise from the third stage shaped in the right way? These interstage quantization terms are first order and second order shaped, and you can control the M and the L to scale them. So by controlling M and L, you basically move the blue guy and the black guy up and down. So move them up and down so that they're hidden below that curve. If you do that, then the relative hardware consumption scales in this way, and it approaches 2/3. So you can save 1/3 of your area with no degradation in spectral performance. Second idea. You have a long word and you're going to a short word through a third order DDSM. I mentioned that when you're using this dither, the way to improve things is to make the bus larger. So internally you're pushing towards larger buses for better performance. But if you have a larger bus, then the throughput is determined by how long it takes you to add large words. If you could shorten the words, you could add them faster and increase your throughput. So that's the idea. Here, we take that bus. We have a large word here. We're going down to a small word. But if we're going down to a small word, let's throw away some of the bits, the LSBs first, and then throw away some of the ISBs, and then finally assemble it. And therefore, this guy, if I have split the bus in 3, for example, this word will only be 1/3 of the width of my original bus, and I should be able to run significantly faster. This is a paper by Park and Cho. It was at ISSCC in 2011 and published in JSSC in 2012. But you'll see they've done something very similar. It started with 16-bit bus and an 8 here, 844 split. Their 844 split, this was the third order block, and then they did first orders here, and these were the spectra that they got from first order pieces. But you'll notice these characteristic spurs here, which are basically coming from the earlier blocks. To do this right, you make sure that these two pieces are properly hidden, and you do it with this scaling. We have an algorithm, and it's published, the algorithm for doing that. Here's an example of what you can do. This is the original 16-bit DDSM, ENOB 19.54, area and power normalized to 1. Here's a 1, 2, 3 split. So we've added a first order shaped piece and a second order shaped piece, but they're appropriately masked. We lose practically nothing in terms of signal to noise ratio, but there's a significant saving in area and in power. And the throughput of this guy, although we haven't implemented it, is potentially 2 or more times faster than the original. This is a piece of work that has just been published. It's in JSSC this month. A conventional Frac-N synthesizer for LTE. We're working off a reference clock 122.88 megahertz. We want to produce 2 gigahertz at the output, so we first try to produce 4 and then divide it down. If you want to do this with the conventional structure, you need int plus frac over mod times 122.88 equals 4 gigahertz. If mod is a power of 2, then you'll find out very quickly that you can't do this. You can approximate 4 gigahertz, but you can't make exactly 4 gigahertz, if that's a power of 2. However, you can cascade another modulator, which is not a power of 2, and by combining these two guys together, you can solve this problem, and you can make exactly the frequency that you want. So here's the conventional structure. I want to make 4 gig, I can't. Here's the mixed radix. So you have a power of 2 here, 24-bit power of 2, and you have 3 here, you can do it. This is the measured prototype. This is without the little extra piece, and this is with. So with it, you can hit the numbers. The structure is that. There's our basic MASH. There's our basic third-order MASH DDSM. Integer plus fractional part, and then here's the second fractional part and the second modulus. Now, as before, this extra term is going to just feed through. It looks like signal as far as the main modulator is concerned, and therefore we have to be concerned about how it shows up in the final spectrum here. So there's that term, but you'll notice that it's scaled by 1 over M1. M1 was a very large number, it's 2 to the 24, so this guy is, that noise is scaled, and you can figure out exactly what's going to happen. There's third order shaped main modulator with first order dither. The worst thing that the little extra piece can do is actually read that tone, but you can figure out where that tone is going to be and make sure it's appropriately masked. Concerning dither, people do different types of dither. This is a paper from 2010 by Malaberti and colleagues, where they have a third order MASH, and they say that if you add dither to the second and third stages, then you can get some interesting results. So here's the theoretical curve that they're aiming for. This is the undithered case. This is with LSB dither, first order shaped LSB dither. But they say if I use a very short pseudo-random number generator, then I can actually get this curve. And this curve is much closer to the theoretical performance than the first order shaped that I get with a very long pseudo-random sequence. And so they say, hey, this is a great thing to do. Now, there's a little problem with this, and here's the little problem. There's the theoretical performance, there's the worst case this guy is going to do. This is the undithered half-scale input. That's the worst it's going to do. Now let's turn on that ideal dither, add it to the second and third stages as suggested. And here's what happens. Yes, indeed, you get longer sequences, but longer sequences aren't enough. You also see the dither signal feeding through to the output. If you look carefully at this picture, you see the dither signal coming through. And we can now predict exactly where that dither signal is going to be and how to design so that it too can be hidden, depending on what you want to do. Okay. The last thing I'll mention is some work we're doing on nonlinearity. Everything I said so far, we thought we were great because we were removing all of the tones associated with the modulator itself. And that's great, but that's, in a sense, completely irrelevant. Because what kills you in practice is not those tones, but it's what happens when the output of the modulator hits a nonlinearity in the loop. And here's an example of that. This is our Frac-N synthesizer again. This is what the quantization noise looks like in time when it's being applied to the input of the phase frequency detector. The spectrum is this classic 20L-1 shape. This stuff here, forget about it for the moment, that's just numerical noise in the behavioral simulator, so forget about that piece. This is the piece you're looking at. So that guy scales as 20L-1. This is the characteristic shape of the quantization noise as fed to the phase frequency detector. Now, if you model a phase frequency detector with, you model a mismatch between the up and down currents here, if you do that, you find that you have this piecewise linear characteristic, and you move, the operating point is here, and the signal moves back and forth along that curve, and it hits this nonlinear piece here. What that does is the time waveform now looks like this, but compared to what we had before, which was just shaped 20L-1, the noise floor comes up, and also you get U-tones. Now the noise floor coming up is well described in the literature. There's a lovely paper by Aurora on that. The tones is less well described, at least the mechanism is less well described, and the connection between that tone and the nonlinearity is less well described. Anyway, that's what we've been looking at. So if you now work this through the system and you say, right, I started with my 20L-1 here, I go through the closed loop filtering characteristic of the synthesizer, and I assume a linear phase frequency detector, then you get more or less this nice phase noise characteristic at the output. But if you hit the nonlinearity, then you see the two effects. The noise floor comes up and the tone appears. And in this case, that's an in-band tone. Loop filtering cannot remove it. And ultimately, this is the thing that kills you in practice. So that's the focus of our attention at the moment. With that, I will thank our sponsors, conclude, and I look forward to a discussion.
A couple of questions. One is, in the conventional analog things, I guess stability was always hard to analyze. How about in this digital case? Can you guarantee stability?
The MASH structure is beautiful from that point of view. Feed forward, unconditionally stable.
We like FIR filters.
We don't even think about it.
The other question was the thing where you were generating exactly 4 gigahertz vis-a-vis 3.999.
Yeah.
But in many cases, you actually want to dither the clock, right? For EMI reasons and so on.
Sure. This specific case, we wanted to hit a frequency of 10.
You mentioned 3 is the best order for hash. Is there a reason behind that?
Okay, so let's see. In the frequency synthesizer application, this guy is growing at 20L-1 dB per decade, and you need to kill it with your loop filter. So if you use a higher order structure, this guy is coming up higher, and the filter order then has to be higher. So you need a higher order loop filter in order to kill the quantization noise from a higher order DDSM. So in the synthesizer application, most people use 3. TI allows 4, but they have a more complicated filter.
I'm just curious, your simulations, were they done using MATLAB or anything, or your own software?
Okay, so the two simulation tools we use most are MATLAB Simulink and Micronauts CPP Sim. So for behavioral simulations, for the full synthesizer, we use CPP Sim.
Can you comment about Marty's idea about forward noise cancellations and quantization noise cancellations?
I'm not familiar with that.
They have a basically feed-forward path. They take the quantization and pass it to charge pump, I think, or
Oh, so okay, so you're saying in the structure, the correction techniques that essentially add correction terms here.
yes.
Uh,
How realistic it is? I know that
No,
it works in simulation.
they're effective, those techniques work, but they're always, I mean, as far as I can see, the root cause of the deterministic spurs that are going to kill you, the ones in band that you care most about, are caused by the nonlinearity. So you can be correcting all kinds of other stuff, but unless you fix that nonlinearity, and that nonlinearity depends on the operating point, which depends on the setting of the value n, and therefore it's not the easiest thing to fix after it has happened. You're better to try and fix that before, and that's why Galton at the moment, or in the past few years, has been doing work on the successive requantizer. So what the successive requantizer is trying to do is, instead of a DDSM, produce another pseudo-random signal, which has the appropriate spectral properties, but when it hits the nonlinearity, it doesn't regenerate these inbound spurs. So design the signal so that when hitting that nonlinearity, it doesn't do this. Because this is a characteristic behavior of the signal that comes from the DDSM.
The technique that you mentioned about odd initialization, is it patented, or you said every company uses its own, or
Everybody, does everybody use it? I've seen it in a Maxim part, Hittite part, analog devices part. I'm not sure if TI uses it, but they may do. I'm not sure anybody patented odd, because that's theoretical work that we did just a few years ago. But they may have patented their own favorite number.
so the idea itself, like
So I would say engineers in practice came to the same conclusion. So they didn't get exactly the same conclusion. They discovered that one of the things they needed was a 1 in the least significant bit. Many thought that they needed the ones in other places as well, or they needed other magic numbers, or some magic numbers were better than other magic numbers. But the fundamental theoretical solution is just that. And in fact, don't miss a chance to sell product. You can learn more about this. So my student cabin is saying, this is our the minimize experienced onset digital delta signal modulator. So all those theoretical results in terms of sequence lengths and initial conditions and so on. I've left the references to this work are all on the stick, which I have left with Dimitri. So if anybody wants to contact him or me afterwards, I'm happy to share everything that's here, and you're free to distribute it to the
Yeah, we'll publish it on the
We'll go on the website, right?
Yeah, we'll put it on the website.
So you will put the slides in the website?
Yes.
Okay, that's great.
Yeah.
Because so many of stuff we cannot.
Yeah, I know.
You know, yeah.
So have you applied any of your chaos to this?
Unfortunately, no.
No?
No, but one of the things, it's very interesting because one of the things we did we had a chaos communications project. And so we were trying to find out, is chaos good in communications? And in order to find that chaos was good in communications or not, we have to learn very efficient techniques for producing chaotic signals, producing spread spectrum signals in the 2.4 gigahertz ISM band, doing all those computations efficiently when you don't have periodic signals, so you have to get baseband. That's where we learned about all this RSUP stuff or USRP stuff. So we learned a lot of things along the way that were useful to this project, but we didn't actually use chaos.
Did you try to apply to minimization of scores to analog sigma-delta converters?
No.
Is there any fundamental reason it couldn't be tracked to work?
Okay. Digital is really nice because we can say odd, even. Okay. The equivalent result. There's a book by Kozek and Clara from Westminster in the UK, University of Westminster in the UK, and they show that the equivalent of this in the analog case is rational, irrational. So if you can set rational or irrational initial conditions on capacitors, you can make it go one way or the other. Now, sorry, that's not practical. Whereas in our case, a 1 or a 0, we can do that.
Thank you. Get dither for free, right? No. Get dither for free. In other words,
You get dither for free. Exactly. So a lot of the things that show up here you don't see in the analog circuits because the dither is for free. Exactly.
Yeah, if there are no other questions, let's thank the speakers. And on behalf of our chapter, we'd like to present you with this certificate.
Thank you.
Thank you.